The topic for today is mathematics in supply chain management. It is part of my series of lectures on supply chain management. Some of the useful mathematical tools in supply chain management include simple arithmetic like ratios, probability concepts, basic statistics, linear algebra, differentiation and integration, mathematical modeling, simulation techniques, linear and non-linear programming, forecasting techniques, and time series analysis, and advanced methods like genetic algorithm, fuzzy multi-criteria decision, or fuzzy AHP. Use of mathematics may be reactive or proactive. Mathematics is used at all three levels in supply chain management, at strategic level, at tactical level, and at operational level. This is my lecture outline. I'll talk about the mathematics in brief, very brief, in demand forecasting, optimization techniques, quality control methods, mathematical modeling, inventory management, logistic management, in supply chain contracts, and I'll talk about a model for perishable products I have taken from a very interesting article. So, forecasting. Forecasting methods may be classified into qualitative methods and quantitative methods. Qualitative methods include Delphi methods or PERT. Quantitative methods include time series analysis and associative techniques such as regression analysis. I have a separate lecture on forecasting. The link is given above. Optimization. Use of linear programming in supply chain management include to optimize routes in order to minimize cost. This is also known as traveling salesman problem. For facility location, we can use linear programming, and we can use linear programming with cost minimization and utilization of supply chain network. I have a separate series of lecture on operational research, some of which include those in supply chain management. Quality control in supply chain management. It includes use of quality control charts for assessing quality of supply. It includes other quality measures of supply, example, time, that is timely delivery. Quality control also includes supplier scoring and assessment. Then use of mathematical models. We can make mathematical model considering price, delays, and risk, etc. I'll talk about one of the model today. And we can also make mathematical models considering inventory cost and other factors. This include AP, IOB, PCS group of models. I have a separate lecture on this group of models. Then inventory management. Three important questions of inventory management include what to order, how much to order, when to order. What to order answer is ABC analysis. How much to order answer is economic order quantity. When to order answer is order point method and order period method. These are two policies for replenishment. Then mathematics include calculation of safety stock and calculation of expected shortage and surplus. I have separate lecture on inventory management, on economic order quantity, on safety stock, on expected shortage and surplus. Logistic management. We can use decision trees for making series of decisions in logistic management. We can measure bullwhip effect. I have a separate lecture on measurement of bullwhip effect. We can use linear programming for identifying quantity to be supplied and from which supplier. Then mathematics in supply chain contracts. This include estimation of amount of product required from the particular vendor, the price of the product, and there is also a model known as news vendor model. Then finally, I'll talk about supply chain management mathematics for perishable products. I have taken from article by this author. The article is very interesting. I will give you the reference at the end of my this lecture. So supply chain network include path. The path may be one or more than one. The path include nodes or facilities, that is point 1, point 2, point 3, and links between these nodes represented in my this example as A, B, C, D, etc. And the nodes include like this node is labeled as point 1, 1, that because this is first path, this is the first node, point 1, 1, then point 1, 2, path is first and the node is second. Similarly, the labeling is for nodes of the second path, and there are these two paths for point 3. So networks may be complex also. So flow through link A, that is flow through this link, is FA, and unit operational cost in link A is CA. So the total operational cost in link A is CA multiplied by FA. So this is the operational cost. Then is shortage and surplus cost or penalty. So if projected demand at node K is VK, however the actual demand is DK, then shortage is DK minus VK and surplus is VK minus DK. So expected shortage at node K is given by this, and expected surplus at node K is given by this term. This K here is subscript. So penalty for shortage at node K, if represented by lambda K minus, and penalty for surplus at node K, if represented by lambda K plus, then total penalty at node K is given by this term. And lambda can be between 0 and infinity. So this is the shortage and surplus cost. Then let us see what is the wastage cost. If wastage at link A, this link is alpha A, and wastage at this link is alpha B, where alpha is between 0 and 1, that is, it is in the form of fraction. So item reached traversing link A is alpha A multiplied by initial items, because alpha is in the form of fraction. If wastage cost is represented by ZA, then ZA depends on alpha A and FA. So for entire path, we can multiply all the wastage fractions, and the quantity which traverses the entire path is this multiplier multiplied by the initial item quantity. So quantity reached or received by point 3 is the summation of all the paths reaching this point 3 multiplied by initial quantities at this path multiplied by the multiplier. So this is the quantity which reaches the point 3. It is summation of quantities through all the paths reaching that particular point. Then there is something known as risk costs. Risk include natural disasters, and risk at link A is represented by RA, and theta is risk aversion factor, then the risk cost is theta multiplied by RA. So the objective is to minimize all the cost, and these include operational cost, wastage cost, total penalty of shortage and surplus, and total risk cost. So we need to minimize these. in a mathematical model. So this is our objective function. We need to minimize this function. So if anyone is interested in further calculations, they can refer to this article. This is very interesting article. So this is all for today. Thank you very much.